Thank you, Gautam, for the introduction. So today I'm going to talk about our recent work on private data acquisition. And this is a joint work with Ali Makhdoumi from Duke Business School, Azarash Malikian from University of Toronto Rotman School of Management, and my advisor at MIT also was there. So the rise of machine learning applications has raised corporations' demand for data. And these companies actually collect this needed data in various approaches. Some companies like Nielsen actually offer payments for users in exchange for their data, while several other companies collect this needed data as a byproduct of their services. But this rapid growth of these data-driven applications has created a major concern about privacy. And in this talk, we are gonna, in particular, focus on one instance in which we are interested to learn a mean of a distribution privately using the data of users. And in particular, we are interested in designing a structure that provides an accurate estimate of the mean while provides potentially different privacy guarantees to different users and somehow compensate them for their privacy losses. Let me elaborate this and further formalize this, our setting, using an example. Let's say a medical institute, which we denoted by platform, wants to learn the efficacy of a drug denoted by theta. There are end users or patients that are interacting with this hospital. And in particular, we denote the medical record of user I by X sub I, which is in the form of theta, the parameter of interest, plus some noise Zi. And for the sake of this talk, we assume Zi are zero mean and IID, and they're bounded by half. And we denote the variance by var. The hospital learns an estimate of theta, denoted by theta hat, as a function of the medical record of these users x1 to xn. So both users and the platform or the hospital want to learn this drug efficacy. The users are the patients that are taking the drug, and the platform is offering the medicine. So they both want to know whether it's an effective one or not. But on the other hand, the users are worried about revealing their medical record xi in the process of learning this estimate theta. And so the question is, how can we learn the drug efficacy theta while we somehow compensate users for their privacy losses? And actually, this article on Financial Times talks about paying patients in exchange for their medical data. This article introduces a company, Humanity, which is aiming for charging pharma companies for the medical data that they receive and pay back to users that own those data. And in fact, this company offers a spectrum of options from the ones that provide the highest level of privacy to the ones that provide the best estimator of the medical parameter of interest. For those who are interested in learning the medical interest and possibly might not care that much about privacy relative to learning that medical parameter. And so the core question here would be that how should we decide on privacy allocations and payments when users have heterogeneous privacy demands? And we are going to study this question and similar questions around private data acquisition in this talk. In particular, we are going to start by talking about the data market architecture when we are aiming for collecting data from privacy sensitive users. We are going to focus on the central and local architectures, and we are going to use the differential privacy framework to quantify the privacy loss of users in both these settings. Next, we are going to talk about the choice of estimator, and we are going to answer this question that given that users might have different privacy demands, what is the optimal choice of estimator here? Finally, we are going to design a mechanism that allocate these privacy guarantees to users with different privacy demands and also decide on payments as a compensation, as a tool of compensation for their privacy losses. And finally, we'll show how we can develop efficient algorithmic solutions to solve the mechanism design problem that we pose. Before jumping to the first part, the data market architecture, I should mention that there is a growing literature on data acquisition from privacy sensitive users. The list of papers here is by no means complete. I've just highlighted a couple of works from the past decade. And due to the interest of the time, I'm not going to go over the details of the works, but I should highlight that while several papers use differential privacy to quantify privacy loss of users, there are a number of papers that use different notions of privacy to characterize the privacy loss of users when we are solving the data acquisition problem. And I should mention that our modeling framework, result, and analysis are different from the papers listed above. Okay, so let me start with the first one, with the data market architecture. So as I mentioned earlier, we are going to consider central and local architectures in this work. I'm not going to define the central and local settings for this crowd. I should just, to set the notation, I should just mention in the local case, each user I passes her data point xi through a privacy channel, which we denoted by c sub I, and then shares this x hat I, which is the private version, with the hospital. While in the local case, in the central case, the users share their non-private data with the hospital. As I also said before, we are going to use the differential privacy framework to quantify the privacy loss of the users. We use the pure DP definition with a slight generalization that we consider the case that epsilon i's could be different for different users. What do I mean by that? We say that estimator theta hat is epsilon I centrally differentially private with respect to user I if the following holds. If I keep the data of all the users unchanged and only change the data point of user I and look at the distribution and the output, I want the distribution to change by at most e to power epsilon I. So it's the classical definition of pure DP with the change that epsilons now could be different for different users, which allows us to capture that heterogeneous privacy demands effect that I talked about earlier. And so since this epsilon I can be interpreted as the privacy loss of the users, meaning that higher epsilon I means that lower privacy guarantees provided to the user, we are going to refer to epsilon I as privacy loss throughout this talk. Similarly, we define epsilon I locally differentially private estimators in the following way, that for the privacy channel CI corresponding to user I, we say that this channel is epsilon I locally differentially private. If I change the input, the distribution of the output changes by at most e to power epsilon. So with now these definitions in hand, we are going to go to the choice of estimator problem that I posed earlier. So let's say that for now, the epsilon 1 to epsilon n are given, meaning that you know that you want to design a private estimator, which is epsilon I centrally differentially private with respect to user i's data. And let's for now focus on the central set. The question is, what is the optimal choice of estimator among all epsilon 1 to epsilon n centrally differentially private estimators? And to answer these questions, we need to first formally say, what do we mean by optimal? And here we take the minimax estimation error. By estimation error, when data of users are drawn from some distribution P, we simply mean the mean square error, or L2 norm squared, of the difference between the theta hat, the estimator, and the theta, the true mean corresponding to this distribution P. And so we assume that this P belongs to a family of distributions calligraphic P. And by worst case estimation error, we mean the supremum over all the distribution, the supremum of estimation error over all the distributions from this calligraphic P family. And finally, when we say an estimator is minimax optimal, we mean that among all the estimators that are epsilon 1 to epsilon n central differentially private, it achieves the lowest worst case estimation error. In other words, the estimator is the solution to this minimax optimization problem. And so we know from the literature in the privacy, several other works by over the past decade, we know that when epsilon i's are equal, the linear estimator with equal weights is minimax optimal. But to the best of my knowledge, there is no result on the heterogeneous case prior to this one. And what we show is that in that case, linear estimator is near optimal up to a logarithmic factor with respect to the number of users. Just to set the notation, what we mean by linear estimator with Laplace mechanism here, let me formally define. Here, the hospital or the platform collects the data of users and forms this sum WI XI, where here these WIs could be potentially different, but WI is basically the weight associated with the data of user I XI. And XI are here just one-dimensional data. And then we add a Laplace noise with parameter 1/8. And so the final estimator would be the sum of WI XI plus some Laplace of 1/8. And so the result is that suppose that epsilon i's are bounded by 1, then a linear estimator with Laplace mechanism is WI eta centrally differentially private, and it's optimal up to a logarithmic factor with respect to the minimax estimation error when we take calligraphic P as the family of almost surely bounded distributions, which matches with our assumption on Zi that are bounded by half. So next, I'm going to try to provide a sketch of the proof that just to highlight the ideas and also highlight that what is different from the case that epsilon i's are equal and what would be some of the challenges that we'll face compared to that case. To do so, let me start with the case that there is no privacy consideration, meaning that the only thing that we need to deal with to get a good estimator is the stochasticity of the data itself, meaning those Zi, those noise Zi in the data. There is no privacy demand for them. In that case, we know that the optimal estimator is the one that puts equal weights on all users' data. And we know that we can get this 1/n by this law of large number type arguments. Now, let's assume that we have these privacy demands in place. And without loss of generality, let's say we can sort this epsilon 1 to epsilon n so that epsilon 1 is the smallest and epsilon n is the largest. This means that the data of user I should have the lowest impact on the estimator, roughly speaking. And roughly speaking, the data of user n could have the highest impact on the estimator. User 1 wants the highest privacy guarantee, lowest privacy loss, and user n can tolerate the highest privacy. So going back to the first part of the result, knowing that a linear estimator with weight WI is eta WI centrally differentially private, the first thing that comes to mind is just putting eta WI equal to epsilon. In that case, WIs will increase proportionally to epsilon i's. But in fact, it turns out that these can be very suboptimal. And we have an example showing that this can be up to a square root of n suboptimal. And the reason is that increasing WI proportional to epsilon I could lead to putting too much weight on a tiny fraction of data. Roughly speaking, it's like you overfeed on a tiny fraction of data from the users that do not probably demand that much high privacy guarantees. And in fact, what we show and what we observe is that the optimal estimator has the following characterization. There is a k for which up to k we increase the weight of the users proportional actually to epsilon I. And then after that, we just cap the weights and do not let them to grow any further and keep them constant afterwards. And this is the estimator that we show. I mean, of course, I'm next going to talk about the lower bound, but this is the structure of the estimator that achieves the lower bound up to a logarithmic factor. And of course, one key question is that how should we tune k carefully, that I'm not going to go over the details of it in the talk. We have the results in the paper. But one thing that I want to highlight, which is kind of counterintuitive for me, is that when we put the weight of users k up to n equal, we are providing equal privacy guarantees for all of them, while in fact, they were not demanding for equal privacy guarantees. So this means that it might be better for the estimator to provide better privacy guarantee than demanded for a fraction of the users, like for instance, for the last user, just to avoid this overfitting issue, which is kind of an counterintuitive observation. So next, to show that this construction that we have is optimal, we need to derive lower bounds as well. And we do so by using Locam's method. So consider two parallel scenarios. In the first one, we assume the data of users x1 to xn are drawn from distribution P1. And in the second one, we consider the case that drawn from distribution P2. For the first case, we denote the distribution of the output theta hat by Q1, and for the second case, we denote it by Q. The idea is that we come up with choices of P1 and P2 that are different so that the perfect estimator should return different values for the mean, but they are designed and chosen in a way that Q1 and Q2 are close to each other, that it makes it hard for the estimator to distinguish. Let me formalize this. Locam's method shows that we could reduce the lower bound method to a hypothesis testing problem between distributions Q1 and Q2, and the error of such hypothesis testing problem is lower bounded by a term that depends on the total variation distance between Q1 and Q2. And so the key question would be bounding the total variation distance between Q1 and Q2. And we developed this bound that depends on the total variation distance of P1 and P2 and the KL divergence of P1 and Q2. I want to highlight one thing about this bound on total variation distance. Note that here we are going to still assume epsilon i's are ordered, epsilon 1 the smallest, epsilon n the largest. Note that here the first term up to some k depends on epsilon i's, but afterwards it doesn't depend on the epsilon. It kind of matches with the intuition that we had from the upper bound that we constructed earlier, right? Because in some sense, saying that up to some k, what is dominating your error is the noise from your privacy, but afterwards, in some sense, this is very similar to the term that you get when you develop minimax estimation error, minimax errors for the mean estimation problem without any privacy. And this is in fact saying that after some k, the main term that you need to control is the error coming from the stochasticity of the data, the zi, and not the privacy. So in some sense, epsilon i's are so large that the privacy is not a bottleneck after that. And so this term, this bound on total variation distance kind of resonates with the upper bound that we constructed earlier. And we plug in this into the bound that we get into the lower bound problem. And the last step would be choosing the P1 and P2 in a way that they are adjusted so that we get the tightest lower. And this is kind of a sketch of the idea for developing the lower. So far I talked about the central setting, upper bound and lower bound. We could define similarly the minimax estimation error and the linear estimator for the local case as well. And we show that in that case, with different epsilon i's, this estimator, the linear estimator, in which each user adds a Laplace noise of 1 over epsilon I user I, and then we take a weighted sum, is optimal. Here there is no log factor gap, and we can show that this is optimal in the local cases. So far we talked about the choice of linear estimator when epsilon 1 to epsilon n were given. For the last part of the talk, we are going to talk about how we endogenize these epsilon i's and how we allocate the compensations. So one could argue, or one could say that we assume that epsilon i's as the privacy loss levels are given, but it might not be easy in practice to demand such a thing from users, meaning that it might not be easy to ask patients to provide their, to know about differential privacy and tell which epsilon I they want to choose differently. Like it might make more sense for the platform to choose it. But with some inputs from users that tell how much they care about the privacy. So we consider a similar setting here. In particular, we assume each user has a privacy sensitivity CI drawn from some distribution F1. You can think of it as, for instance, the medical app that collects your data asks you how much you care about your privacy from 1 to 5. 1 is the very low and 5 would be the very high. And this would be the CI that you report. And CI, as we will see later in the definition of the user utility, is the per unit cost of privacy loss of use. But one immediate thing that comes to mind is that when users report their CI as their privacy sensitivity, they might report a different value. They might report C prime I different to CI in the hope that they keep their data private, but hoping that the efficacy of the drug will be learned through the other users' data. A problem similar to the free riding problem in economics literature. So in the original paper on mechanism design from Meyerson, it is shown that the revelation principle, a result is shown known as revelation principle, which says that we can always focus on mechanisms that are direct and truthful. What does it mean? Is that we can always focus on mechanisms in a Nash equilibrium in which all the users report their CI truthfully, meaning that CI prime will be equal to CI. We show such a revelation principle holds in our case as well, meaning that we can only focus on the case that CI are all reported truth. So to formalize this, let me first pose the mechanism. So far, we said that we have user 1 to n, their data are drawn from some distribution, and each user has a privacy sensitivity CI. The users report either xi or x hat I based on central local architecture, and they also report C prime I as their privacy sensitivity, which could be in theory different from CI. And the mechanism has 3 outputs. First, the mechanism returns a function ti, which is the compensation paid to user I that I talked about it earlier in the first few slides. Second, the mechanism will return epsilon I as the privacy loss level, differential privacy epsilon parameter corresponding to user I, and these are functions of this reported C privacy sensitivities. And finally, the linear estimator, the optimal linear estimator, is the last output of the mechanism. And in some sense, TI as the payments and epsilon I are the tools that should design such that users are incentivized to report their privacy sensitivities truthfully. But when we talk about incentivizing users, we need to have a utility function to formally pose such a constraint. Let me next say what is the utility of the function. So the utility of, so here it's easier for us to work with the cost function. And so the cost function of a user, which is a parameter of all the privacy sensitivities, epsilon i's and everything, has made 3 terms. The first term, as we said, is the mean square error, because the users derive benefit from accessing to a better estimate. So the first term in their cost is the mean square error of the estimate. The second term is the privacy cost. And here, the privacy cost is the CI, their privacy sensitivity, times epsilon I, which is their privacy loss level. So that's why we earlier mentioned the CI can be interpreted as the privacy per unit privacy cost. Of course, here we only focus on linear functions. One could generalize these to nonlinear functions of CI and epsilon I, but here in this work, we focus on linear privacy costs. And finally, we subtract the compensations that users receive. And these 3 terms together will be the cost of user I. And of course, we need to define the outside option, meaning that what will happen if users just simply do not join our trial, for instance, for learning the drug efficacy. In this case, there would be no privacy loss and no compensation. So the second and third term will disappear. But the first term, here we make an assumption that if they do not participate, they will not have access to the data hat. So the best mean square error that they can have is just by going with their single data point, where in that case, the mean square error would be just simply variance of one data point, which we denoted by var. So the outside option of not participating in this and not sharing the data would be just var. So now we have the user's utility, we have the outside option, we are ready to pose the platform's problem. So the platform has 2 simultaneous goals. First, to find the best estimator, and for that wants to minimize the mean square error. And second, wants to pay the lowest possible amount of compensation to users. Here we just simply add them up. You can think of weighted sum, and this analysis will go through similarly, but for simplicity here, I'm going to just take that the platform wants to minimize the sum of mean square error and the payments. But there are 2 constraints here. The first one is called incentive compatibility in mechanism design literature. And what does it mean is that if the users all reporting truthfully is a Nash equilibrium. Here, the constraint is the following. If all the users report truthfully, the cost of user I is minimized if she also reports truthfully. So in other words, all users reporting their privacy sensitivity truthfully is a Nash equilibrium. The second constraint is called individual rationality in the mechanism design literature. And what does it mean is that the cost of user is better than the outside option that we just discussed, meaning that the user has the incentive to join and share her data rather than just going with her single data. So the platform's problem would be finding the best estimator and finding the best epsilon 1 to n and t1 to n that minimizes this minimization subject to these constants. And you can see that this could be a challenging and non-trivial problem because first of all, this is non-convex problem, and second, we have three functions that we need to minimize over them, three sets of functions. But on top of that, these are entangled, right? Because your choice of estimator will affect on your privacy loss levels epsilon I. Your choice of weights will affect your privacy loss level. And the change in privacy loss level will change the compensations that the users receive. And so we need to somehow minimize them, but they are all correlated with each other. The first step in solving this optimization problem is that we show that we can somehow get rid of these two constraints here and replace them by a characterization of TI. In other words, we characterize TI in a way that satisfies these two constraints and has the minimum possible value. So we can just substitute it here. I'm not going to go over the details of it, but after doing so and removing these two constraints, we get this optimization problem. Let me for a second explain a few terms here. The first term that you see, the new term, is this psi I that is generated by this characterization of TI, and it's called virtual cost, which is the sum of C, the original privacy cost, plus a term that depends on the CDF over the PDF of the distribution. So this is a term known in the some auction literatures, and different variations of this appears in different problems. Sometimes in original Meyerson problem, you see C minus here, but in procurement auction, you see C plus the PDF over CDF. And this is called the virtual cost, which is the sum of the original cost plus the PDF, CDF over PDF. There is also an additional constraint that you will see. So we remove those two constraints, but there is a new one popping up here, which is the result of that characterization of TI, which I didn't go over the details of it in the slides. But if you do so, you will need to have these constants. But again, this problem doesn't seem that much tractable. Okay, we got rid of one element of the optimization, but these constraints doesn't seem that much easy to deal with because it's like a expectation being decreasing in one term. And also we have this expectation here, which could make the optimization problem hard. But we have a proposition that shows that assuming that these virtual costs are increasing, which holds for a variety class of distributions, like any log concave distribution, we can show that actually we can drop this constraint and we can solve this optimization problem pointwise. And the solution of that will be the solution of this original optimization problem that we have in hand, which makes the thing much easier. It means that now the only thing that we need to deal with is this inner thing inside the expectation. We need to just minimize it for a given vector of C1 to C1. And this proposition says that solving it is equivalent to solving this more complex problem. So this part of the technique is known in the mechanism design literature. But in the classical mechanism design, using this technique, what you see is that you get a linear optimization problem, for instance, in the original Meyerson 1981 mechanism design paper. While here in our case, this is not even nonlinear, but actually non-convex optimization problem. But what we show is that using this architecture of linear estimator, we can further simplify this term and get a more tractable problem for the central and local architectures. Let me start with the central set. The result that we have is that we can reduce this optimization problem to this given optimization problem here, this expression here for the central set. For any reported vector of privacy sensitivity C1 to Cn, what we need to do is to solve this optimization problem, where epsilon I is just the privacy loss level allocated to user. Still, this problem is non-convex, but in fact, it has a structure that allows us to develop an algorithm that solves this problem in time n log n. For the local case, we get again, a problem, depending only on epsilon I, and it's still non-convex. And the result that we are able to show is that we develop an algorithm that is delta approximate optimal in time polynomial in n and 1 over delta. The fact that whether this polynomial term can be improved to a linear or quasi-linear term is still some open problem to us. So we don't know whether this can be further improved, but we have a polynomial time algorithm for solving this problem approximately. Okay, so for the last part of the talk, I'm gonna say that so far I talked about optimal mechanism design problem for central and local case separate. One natural question is that how do they compare to each other? And to answer this question, you need to answer it from the perspective of the platform and the users. From the perspective of the platform, what we show is that the platform always prefers central differential privacy. What does it mean? It means that if you compute the optimal cost of the platform under both central and local cases, the optimal cost would be always weakly smaller for the central case, which intuitively makes sense because in the central, they get the platform gets the non-private data and decides on adding noise herself, rather than in the local case, users add noise in advance before sharing it with the platform. However,
Alireza, sorry, question. Isn't the local model like just it's a subset of the algorithms, right? So isn't, like, maybe I misunderstand the statement, right? Like in one case, you're optimizing over a larger set of algorithms, so you potentially get better outcomes, right? That's the content.
Why is that?
Like locally differentially private algorithms are central differentially private.
Oh yeah,
They can be interpreted. Like you can just run the local, like the central server can just run the local.
Yeah. That's okay. That's a very good question. That's correct. So the thing is that but we are restricting ourselves to a class of estimators. So locally differentially private linear estimators are not necessarily equal to a linear estimator in central case with Laplace mechanism.
I don't understand.
So, okay. So
what do I mean? In that case, I don't understand the proposition.
Yeah, okay. So what do I mean is that if you take a local linear estimator with Laplace mechanism, a linear one, so what you have is that each user adds a Laplace noise and then you sum it up with some weights, right? Okay. So if you rearrange this, you will get a linear estimator with sum of some Laplace noises.
Yeah.
So this is not immediately equal to a linear estimator with one Laplace noise, which is the central architecture. Here, the one that we consider.
I see. So the proposition holds for, like, in both cases, a subset of algorithms.
Yeah. You're right. This is a kind of an informal version. Yeah. So in the case we focus on linear estimators and that particular architecture that I showed here. So this one, that you take this sum and then add Laplace noise, one Laplace noise, and in the local case we take this one, that each one adds a Laplace noise, and then you get this on. Then for this case, yeah, this proposition holds. In general, you're completely right. The local estimator is always central. So this would mean.
Okay, thanks.
Yeah. So this was for the platform's perspective. For the user's perspective, users actually may prefer central or local depending on their privacy sensitivity. So this is kind of also intuitive. When a user has a small privacy sensitivity, it means that probably they do not care that much about their error. They do not care that much about their privacy. They probably care much more about learning data. So they would prefer the central setting. But when we have a high privacy sensitivity, meaning that they care a lot about their privacy, they would prefer the local case. So with this, I'm gonna wrap up this talk. So the main two takeaways that I would personally like from this to be remembered maybe from this talk, one is that this is kind of just an attempt to provide a structure for private data acquisition when users potentially have heterogeneous privacy demands. And so how could we think of providing still a good estimator, but at the same time giving different privacy guarantees and also coming up with some sort of compensations, which is a problem that is getting more and more attention in the data market type research in econ and operations research. With that, I'm gonna stop here and thank you very much.